Aunque ya me decía que hace, ¿qué? 5 años, ¿verdad?
5 años.
La vez pasada. Él nos va a hablar sobre la electrónica y el grafeno, la electrónica del grafeno. Y tenemos una petición de que nos dé la charla en inglés. Las láminas están en español. Entonces, si no hay nadie que tenga una objeción, entonces le pediríamos a Gerardo que hable en inglés.
Bueno, muy bien.
Y bueno, pues gracias, Gerardo.
No, de nada, gracias, muchas gracias a esta invitación. ¿Qué prefieren, esta o esta? ¿Sí?
Sí, mientras no le des al techo, ni a la primera fila.
Bueno, muy bien. Bueno, ok. Entonces, okay, I'm going to talk in English. So the title of this talk is Toward a New Electronics Based on Carbon. This is the graphene. So this work was made with Francisco López Rodríguez and José Eduardo Barrios Vargas from the Institute of Physics. These were my PhD students. And let me start a little bit. This is the outline of the talk. I'm going to give an introduction about why it's so important graphene and why there's so much talk about it. Also, we're going to talk a little bit about the Nobel Prize. Then we are going to talk, if we have time, about all these topics that we have been working in the Institute of Physics. Basically, we have been working with defects of doping. Then we also studied electromagnetic waves on graphene. Also, we studied electrical resistance in graphene, and especially we proposed a Dirac equation in Cherney space because we are going to see one of the most exciting things in graphene is that the dynamics of the electrons are described by quantum relativistic equations. There's a big history about that, and if we have time, we are going to show some designs that we made concerning nanotransistors and nanowires, and then we are going to give the conclusion. So let me start just a little bit with some reflection about the importance of carbon in new materials. So this is the, some years ago, Airbus was making this plane that it was supposed to be to replace one of the medium range planes, and they proposed this design based on aluminum with lithium. But Boeing at the same time proposed this airplane, which is more or less similar to this one, but this one is almost completely made from carbon fibers. Yeah. So in fact, nobody wanted this plane, and eventually Airbus went to redesign this plane, and they lost something like 4 or 5 years. So this thing completely won the market because this company was not able to produce something with this new technology. And in fact, these are some words that the director of the company of Boeing said that the future is plastic. So basically, nearly 50% of this airplane is made from this composite made from carbon. So this was a huge lesson because nobody thought that it was possible to build a plane made from plastics. And eventually, of course, there are many difficulties, but there are many advantages. If we look at a traditional plane, we can see that they are built by small plates of aluminum. These take a lot of work because you need to solder and everything. And if we look how this new plane is built, it's basically it's made just by how do you say it, by wool?
Spinning?
Weaving? Weaving the fibers. So in fact, they cut, for example, the windows and so on. So there are many advantages. The first one is obvious, is that the carbon is much more, is lighter than aluminum, and everybody knows that carbon bicycles are much better than aluminum, much better than the iron, but of course the price is higher, but this is due to the technology basically, not due to the material. But the price and the difference is huge, having a composite bicycle. So it's the same in history here. There are other advantages. For example, this is more resistant than this for the compression cycles. So for example, this this cabin can be pressurized at a higher pressure, and that's much better because also the content of humidity in the plane is not much better. The windows are bigger here because also they think it's more resistant to this kind of stress. So there are many advantages compared to this one. There are other disadvantages. For example, if a lightning strikes this plane, this is a huge problem because there is no way of, this is not a Faraday box, so they need to put some wires inside it to avoid that problem. But in fact, Airbus thought that this was not possible to build this plane, and now it's flying. Of course, they had a lot of problems, but eventually here's the plane.
The radar is transparent?
No, the dome of in all planes, the dome is made from a different material. In any planes. If you look at a real aluminum plane, the dome of the radar is made from, I think, glass fiber. It's completely, it's not. The same thing here, you can see it here. The cone of the radar is not here. Yeah. So this is a big lesson. And this is interesting because if one look at the table, periodic table, is obvious why carbon is so important. Because here with hydrogen and helium we can't do any solid. But with lithium beryllium they are very soft. So we end up with boron and carbon. Yeah? And of course we know that carbon, for example, one can make diamond, which is a very strong material. And that's the huge importance of carbon, of course, in life. But there is another interesting thing. We have been we learned in the school that the elements that are in the same column of the periodic table, they share the same chemical properties. And if one look at the silicium, we know that the electronics is made from silicium. So it's very pertinent the question of why is it possible or not possible to make a computer made from carbon. And of course one can say, well, in fact, it's possible. Our brain is made from carbon. Yeah? So it's possible, of course. So the question is why we are using computers made from silicon, and if it's possible to make computers of carbon, do they have any advantages or not? So this talk is concerned with this question. Why, or is it possible or not, or that's the idea. So, and in fact this is interesting because if we look at the technology of computer science, technology of computers, we can see that in fact most of the advancement in the technologies was just the ability to make transistors smaller. So this is the first transistor. Yeah? You can see that it's more or less the same of this guy, I think is Barbino copy, I don't remember. But this is a very famous photo. Yeah? So here we have, in the 70s, they were able to put all these transistors in these areas. Yes, so for example, these integrated circuits, they have thousands of circuits. But then, in the 80s, 90s, we arrived to make, it was possible to make and to put into a given area millions of these transistors. But basically, the material is the same. So in fact, there is a very well-known law that is called the Moore's law that tells you that the number of transistors that you can put in a certain area doubles each 14 months, something like that. I don't remember 14 or something like that. That means that the growth is exponential. So if we put here the year, so this is the 70s, 80s, 90s, 2000, and here we have the logarithm of the year, and we have the logarithm of the number of transistors. They follow a straight line. So basically it's a power law. And in fact, for example, here we have Pentium 1, Pentium 3, Pentium 4, etc. And so on. It's very interesting because in fact it was possible to extrapolate this graph to other computation, in mechanical computations, or using, for example, hand machines. So in fact this is very interesting because one can go many centuries ago in the power computing. Eh?
One can go to the past.
To the past, okay. Exactly. That's interesting. But the point is that we have Pentium 1, Pentium 3. So for example, each of these ones are chips of the Pentium 4. So these are around 40 nanometers. And now they are producing transistors of around 20 nanometers. But there are many problems. The first one is that they are reaching a physical limit, because with silicium, it dissipates a lot of heat in each transistor, and in fact, that makes the how do you call it? The surface of the transistor, the interfaces inside the transistors, very unstable. It's like a frying pan, like putting a drop of water in a frying pan. Yeah, it evaporates, in fact. So they have a lot of problems with that. There's a lot of leaking of the electrons. And in fact, one can see that because in recent computers, one can buy processors, double, quadruple, things like that, because it's really getting very difficult to scale the number of transistors inside a given area. So that's why we are using this double, quadruple core and that kind of thing. But the problem is that in order to use that kind of things properly, to really use that kind of double and quadruple core, one need to change the software, try to parallelize things, and that's much more difficult. One really wants to make very small transistors. So we are reaching a limit, physical limit, using silicium. So there is a search for new materials in this field of electronics. If there are any questions, please. So basically, now I want to talk about a different story that seems to be not related with this one, but this is about, in fact, about nanotechnology and carbon allotropes. In fact, the big rule of carbon began with the discovery of the buckyball by Henry Crotta in 1985. And this is, I put it here, and this is like a zero-dimensional structure because it's like a dot. But of course we know that with carbon we can make, this is a very good example, especially for students, about how the structure can determine the properties of a solid. So for example, if we put carbon has 4 electrons, and one can hybridize s electrons and s orbital and p orbitals to have this sp3 bonding, when each electron is shared with another carbon, and this orbital goes to the direction of a tetrahedron. Then one can make diamond, which is the most transparent material, the best isolator, is very strong, one of the strongest material, and also is one of the most expensive. On the other hand, one can also use with carbon, if these orbitals hybridize in this way, so we have, in each plane we have covalent bonding in the plane, because we have 3 electron pointings to the direction of a triangle, and we have 1 electron here that is almost free. This is called the sp2 orbital, and this is going to be very important for us. Well, we can have graphite. Graphite basically is just a piling of 2-dimensional sheets of carbon in an hexagonal lattice. And this material is black, this is metallic, and this is very cheap, and also very soft. In fact, we use it to draw, we use them in pencils, because this is very soft. So it's very expensive, very cheap. Now, this is 3-dimensional materials. So this is also very interesting because this material is very, when one writes, the interaction between these planes is not very strong. So in fact, all these shades are peeling away when one writes due to this thing. So basically, this is going to be interesting for us because we have 1 free electron here, so the interaction here is very weak inside the plane. So eventually, in 1993, the people discovered that it was possible to make nanowires, 1-dimensional nanowires. But nobody thought that it was possible to obtain only one sheet of carbon, basically because there is a theorem, we are going to discuss a little bit, there is a theory in statistical physics that says that it's not possible to have an ordered system or a system with a long-range order in 2 dimensions. This is called the Marmin-Wagner theorem, and there are many formulations. So, in fact, in 2005, this material was discovered. And it was discovered in a very simple way. I'm going to show you how they discovered this material. In the computer algorithm. So it's very surprising. We are going to see that it's very easy to win a Nobel Prize. Well, everyone can do it. But the important thing is to be the one to do it first. Yeah? Okay, so basically, they took carbon and they used a Scotch tape. So basically, one puts a Scotch tape, put the carbon inside the Scotch tape, and you do that way. So basically, you are peeling the different layers of graphene. Sorry. So you do it after you get something that is nearly transparent. Then you transfer to a quartz wafer. And then we need to put this wafer inside an optical microscope, and just by interference it's possible to see that the one layer graphite, which is basically the graphene. So basically it's just a plane made of one atom of thickness. It's here. So in fact it's very easy. Surprisingly easy. So they won another prize. Of course, they characterized it very nicely the material. And they found a new quantum Hall effect that I'm going to explain a little bit. Why there is a different quantum Hall effect. Okay, here we have the graphite, how it looks, the graphene, sorry. And in fact, when one write, they discovered that in fact there are many graphene layers. So basically, the people began to measure, for example, electrical conductivity, because this opens a new directions, because it's the first truly two-dimensional material. And there are a lot of interesting things. So, for example, they measured here the electrical conductivity, and they observed that this material has the highest known electronic mobility, which takes into account different factors. So, for example, velocity of the electrons. The velocity, in fact, of the electrons is the velocity of the light divided by 300, and also the density of electrons. Many different things. But the thing is that it has the highest mobility, electromobility for any material. Also, it has the highest thermal conductivity. So it means that one can the heat. I don't know how to say this. The heat, one can float very easily, but that's a good thing for making electronic devices, because it's very easy to cool it, because one can remove the heat very easily.
But why is the conductivity, your electronic or heat conductivity, better in graphene than in graphite?
The explanation is very simple, because electronic conductivity depends on the interaction with the vibration of the lattice. So That's
But
called
they're
phonos.
almost free.
I want to explain it.
But they're almost free, no?
In where?
In graphite.
They're almost free, but you certainly have another direction. You have interaction. Here you will remove any other interaction with the up and down. It's like the difference between living in a house and an apartment, you know? Because you have noise all the time. I know it because I used to. It's a huge difference because you have noise. Yeah. So in fact, they discovered also that this the strongest material, and of course, it's bidimensional. It has a lot of many properties, and also, in fact, there is a discussion why the Nobel Prize Commission gave this prize to this guy, because there are many promises, yeah, but the question is, well, is it really so interesting? And the question, yes, because there are many new physics, I'm not explaining why, new physics and a lot of new technological applications. So that's why it's so important. It's one of the hottest research topics in the world at this moment. So, but first of all, it's because it's the first two-dimensional crystal. In fact, it violates a fundamental prediction that is in almost all books of statistical mechanics. Is the Wagner-Manning theorem. Also, Landau working a little bit. He said that it's not possible to have long-range order in two dimension or in one dimension. The same because any thermal fluctuation destroys orders. It's like it's not possible to have a ferromagnet in one dimension because any thermal fluctuation just destroys all range order. So that's very interesting. But also there are other important things. First, of course, it has the highest electromobility at low temperature. This is the lowest resistivity substance node at room temperature. Also here, very important, it has a huge coherence length. Usually, in a real material, it's not possible to see quantum effect because the wave function loses the coherency. Because there are collisions, and so basically one sees an average. But here, it's possible, even at room temperature, this coherent length is around micrometers, which is huge. So one is a complete new word for observing quantum phenomena. That's one of the most interesting things here. Also, there is a huge discussion because one observes minimum conductivity in graphene. That means that.
Para calcular la productividad, ¿qué área toman en cuenta por la movilidad?
¿Cómo?
¿Qué área toman en cuenta?
No, pues justamente esto está tomado por unidad de área, ¿no?
Pero es una cosa bidimensional y tiene huecos en medio.
Entonces, ¿Cómo que huecos en medio?
Pues así como lo dibujaste en la...
¿Dónde lo dibujé que dibujaste?
No, en la fotografía que pusieron por ahí. Antes. Ahí.
Los hexágonos.
¿Los hexágonos qué?
Para la conducción, digamos, es para arriba, ¿no? Entonces...
No, la conducción es sobre, básicamente el electrón va saltando de un átomo a otro así.
¿Y el área? ¿Cuál es el área de conducción ahí? ¿Cuál es el área de conducción?
El área de conducción es sobre el plano. El electrón se va moviendo sobre el plano.
La sección transversal de conducción, ¿cuál es?
O sea, tú lo que dices, pues es prácticamente cero, pues es nada más una capa de átomos, es un área, o sea, no es un volumen, es un área.
Pero tuvieron que haber puesto un valor, ¿no? Para calcular conductividad.
¿Cómo?
Tuvieron que haber puesto un valor para calcular la movilidad y la conductividad.
¿Un valor de qué dices?
Pues del área de conducción, de la sección transversal.
No, claro, pero eso está tomado por unidad de área, lo hacen por unidad de área, o sea, mides el área, no, la longitud de los dos lados, mides el área, ¿no? Tienes que medir la concentración de portadores, la velocidad, etc.
Pues hay una confusión con el área transversal a la corriente, ¿no? Que en este caso es un átomo de...
Sí, es un átomo de espesor, bueno, no sé, es 2 átomos.
Pero es conductividad superficial, ¿no? Conductividad superficial
sí.
Con otras unidades.
Bueno, además eso lo miden experimentalmente, ¿no? Pones el campo y lo mides, ¿no? Es como lo midieron, es como que demostré, pone 2 electrodos. Además está suspendido el grafeno, ¿no?
Sí, pero para dar los valores hay que poner ciertas constantes, entonces ahí quién sabe cómo se toma eso.
No, pero yo digo experimentalmente, ese resultado es experimental, cuando se midió es un resultado experimental.
No,
Cuando pones el campo...
Es que mides corrientes o voltajes, pero parámetros geométricos están raros.
Bueno, Luego lo discutimos si quieren. Bueno, entonces, why graphene? Why graphene? First of all, because there's new physics. Especially we're going to see that electrons behave like massless Dirac fermions. That means that they behave like neutrinos with zero mass. And this is very interesting because there are a lot of phenomena that are not possible to be observed in, let's say, rate or something like that, and one can observe them in graphene. Yes, and that's very nice because this is one of the reasons why they gave these guys the Nobel Prize, because there is a new quantum Hall effect that is different from the usual quantum Hall effect. The levels go different. And of course there are new novel devices. There is a promise of novel devices because of this characteristic. Long mean free path, high conductivity, initial transport is inert, high strength, composite, and so on. So let me start. So those were the good news, but the bad news is that, okay, just before. So basically this is very nice for replacing silicium because it has a very high electronic conductivity, mobility, a long mean free path, and that means that the heat can be removed very easily. So this is very desirable for it. But the problem is that silicium is a semiconductor. That means that there is a gap in the energy. We're going to see that one. But graphene, it's a semi-metal. In fact, this has a very particular dispersion that it makes this material related with these massless Dirac fermions. And this is very interesting because this kind of density of states is also very interesting because there is a huge new kind of material, the topological insulators, which is also a new topic of research that is related a lot with this kind of things. So basically the idea is the following. Usually, here if we have the energy, we know that in a usual semiconductor like silicium, all levels are filled till a level that is called the Fermi level, and there is here a band gap that separates the electrons that are in the valence band to the electrons in the conduction band. So in semiconductors, this band gap is it can be thermally activated. It's not huge. In the case of isolator, this band gap is huge. In the case of a metal, this thing is like this. But if we look at graphene, we are going to see that in fact the valence and the conduction band, they touch in a point. In this point, it has a singularity that is called the Dirac point or the Dirac point. And all these properties, and since the Fermi level happens to follow inside this singularity, that's why the properties, electronic properties, are so special for this material. So basically, in fact, this idea of considering graphene as if it's electrons in graphene as quantum relativistic fermions, in fact, it's a very old idea because the people studying graphene since the 40s, especially because graphene is used for the moderator, how do you say in English, moderator? Nuclear reactors. Moderate chain reaction in the nuclear reactors. So you have these rods that folds inside the nuclear reactor. So there was a lot of research on graphite due to that. And in fact, one can solve very easily, for example, the Hamiltonian for the electrons. I'm going to show just a little fast slide, but the idea is that one can solve this thing using something that is called the tight binding approximation. One can suppose that the electrons are well localized, so basically one proposes that the Hamiltonian of the graphene is basically by the sum of Hamiltonians centered at each atom, and these the orbitals are just these molecular orbitals, and this can be solved using this tight binding approximation. Basically one proposes a solution which is basically a linear combination of solutions of each individual atom. And this is called the tight binding approximation. This is very well known. The only thing that one needs to do is that one needs to remind that in fact graphene, this is going to be important, this is not a Bravais lattice. This honeycomb lattice is made from two kinds of atoms. So for example, the red one and the blue. because one can see that if one of the definitions of a Bell lattice in a crystal is one need to see the same thing in all places. And here is not the case, because if I see it in the red atom, I see a blue here. But if I'm sitting here, I see a red atom here, in the other direction. So basically, this is basically a lattice that contains two kind of atoms, and this kind of lattice is called a bipartite lattice, because if I start in a red atom, if I jump to my neighbor, it's always going to be blue. And this not happen if I'm, for example, in a triangular lattice, in which this is connected with this, because I can jump from here to blue, and this is not bipartite. And this is very important for the properties, in fact. In fact, this is the whole history hidden. But basically, one needs to propose two solutions, A and B, and eventually it happens that one can arrive to this thing, and this is called this is the electronic dispersion relationship that gives you the energy of the electrons as a function of the momentum. Since this is a one-dimensional, two-dimensional system, we have momentum in the direction x, in the direction y, and here we have the energy. So basically, this is the dispersion relation for graphene. And there's a very interesting thing. Here we have this part, the lower one. These are the electrons in the valence band. Yeah? And so all these states are filled here. And this is the conduction band. And they touch in these points, these singular points. And here we have an amplification. This is not good. This is the valence band, and this is the conduction band. So the Fermi energy happens to be here. And here, these two, they touch in a point. This is called the Dirac point. The Dirac point. And this is very interesting because, first of all the electronic properties are determined by electrons that have energy around the Fermi energy. And this is interesting because, for example, in semiconductors, the band edges are always, they have a parabolic shape. But here, they are linear. And in fact, that means that if I look here around the Fermi energy at the relationship between energy and momentum, it happens to be given by this. No? It's just the momentum multiplied by the Fermi energy, which is basically the slope of this energy. Yeah? And we have two signs here also, which is interesting because here we have electrons and here we have holes. Then it's interesting because if one reminds the relation between energy and momentum and relativity, this is given by this very famous formula for Einstein. We know that, for example, for usually one can develop the thing, and at low temperatures one obtains the famous, the usual classical expression that the energy goes to the momentum to the square. But in the other limit, in the ultra-relativistic limit, or which can only, the ultra-relativistic limit is obtained for particles that fly at the velocity near to the velocity of the light. And this happens to be, if one puts the mass equal to 0, this happens to be that the momentum is proportional to the, it's just energy is proportional to the momentum multiplied by the velocity of the light. So basically one sees that this is the same relationship. The only difference is that the velocity of the light is replaced by the velocity of the Fermi, which is around c over 300. Yes, so and in fact,
the fact that you have these conical bands depends only on the symmetry of the lattice, of the 2D lattice?
Yeah, basically yes.
Not on the details of this Hamiltonian shores.
No, basically on the symmetry. Yeah. And in fact, you can, now the people discover that you can make other different materials, boron and things like that, using these kind of ideas. And also interfaces, which are topological isolators. There is a huge, of course it's a new subject, topological insulators, but basically happens the same thing. At the Fermi energy one also have these kind of things, topological. The difference is that, just for the people that want to know this, in the beryllium zone we have here 4 Dirac cones. And in the topological insulator one only have 2. That's very different. So it happened, in fact one can show from this tight binding, one can show that the effective equation for electrons It's just given by this equation, which is the Dirac equation for relativistic massless particles. It's the old neutrino, because it was believed that they didn't have mass. So basically, we have here the velocity of Fermi velocity at the Fermi level multiplied by this. And of course, we know that the Dirac equation has 4 components, because we know that each particle has 2 spin, 2 degrees of freedom, and antiparticle. So for example, the electron has a spin up, spin down in its antiparticle, which is the position. But here also, this idea works perfectly, because here we have the particles are the electrons. Here we have the antiparticles, which are the holes. That means that if we remove an electron here, we produce a hole, which is a vacancy. So it's the antiparticle. And also the role of the spin here is played by something that is called the helicity, which is basically the projection of the momentum around the projection, well, it's the helicity. The helicity
on the momentum.
The spin on the momentum direction. Can be in the direction of the movement or in the other one. So basically, what we don't need to worry about it. The idea is that the Hamiltonian goes like this, and this is very interesting because in fact this leads to a new quantum Hall effect. In the presence of a magnetic field, things are different. But this is a very bad news for using graphene in transistors, because there is something that it's called the Klein paradox that appear in quantum relativistic mechanics. Is that if we have, for example, in classical, let's say classical, not classical, or non-relativistic quantum mechanics, if we have here a variable potential and we send particles, the particle has a certain probability of tunneling here, and it can go to the other side with certain probability. But it happens that when this one have a relativistic particle, in certain directions, one can have that this thing is going to be transmitted with probability 1, because for even if this potential is repulsive. And this is exactly because in relativistic quantum mechanics, particles can change to antiparticles. Yeah? So one can change. So if this thing is repulsive for this thing, for the antiparticle is attractive. And since the mass is 0, one can generate a pair. This is related with pair creation. And here it doesn't cost any energy, because pair creation, the energy is m multiplied to the velocity of light to the square. And here the mass is 0, so there's no energy needed in order to create a pair. So that's bad news, because usually for a transistor one need to have a source of electrons, one have electron flow in a train, and one control the flow. So the idea is how to control these things by using this kind of thing. And I'm going to show you just a flavor of the thing that we are doing, because we are doing many things, but basically I'm going to say a little bit about doping effects, because we say that these ideas work very nicely only if the potentials are huge. But if one considers local disturbance, like for example chemical doping, the graphene, things change, and this Dirac equation needs to be changed a little bit, and eventually it turned out that one can produce a semiconductor, a narrow gap, and this has been measured for other people. We made a prediction, and in fact it's true. I'm going to show why. Then I'm going to talk how to treat electromagnetic waves. Basically what we did is to consider a two-dimensional system with a Dirac equation and solve the Dirac equation in 2 dimensions with an electric field and other things. But let me start with this one. So basically the idea is very simple. We considered this graphite, and we put some impurities. And basically the thing that we did is, well, we considered the Hamiltonian of pure graphene, and we introduced some impurities. So for example, it can be hydrogen, lithium, something like that. It works better with light elements. So basically we put these things at random with a certain